Okay, let's begin. So we're continuing with related rates. Continuing with the handout. Ask you guys to do 3 of these problems. So let's start with problem 7. Someone tell me what to do from this group over here. Yep.
First I drew an upside down triangle. So like.
Well, what is the first thing you're supposed to do? Read. Read very carefully, right? It's going to be one of those word problems where the details will matter. Okay, so assuming you've read the problem because you actually did it, a water tank has the shape of an inverted circular cone. The base is 3 meters, the height is 9. It starts out filled with water. Water is leaking from the bottom at a rate of 2 meters cubed per minute. We want to know how the radius of the remaining water is decreasing when the radius is 1 meter. Okay, so yeah, what was your...
I drew like the cross section of it, so like an upside down triangle.
Okay.
And I labeled the, like I put a dot in like the center of the top line, and yeah, that's 3 meters. And then you could like mark the height as 9 meters. And then somewhere like along the middle of the triangle, like there's another line, which would represent like the new water level. And
okay.
the radius of that line is 1 meter.
The radius is what?
1 meter. And then I went to like the no and the 1 portion.
So that's your fully labeled diagram? What were the rules for labeling? What was the rules for labeling? How do we label something?
Oh wait, the radius is changing, so you would label it R.
Right, you wouldn't label it 1, you would label it R, because that is changing. What else do we care about here?
The height.
The height of
the water.
The water. So you should probably also label that.
Yeah, make it H.
H, because it is changing. Anything that is changing, you label the variable. So that's a nicely labeled diagram. So that's what your step 2 should be. Now, 3, what do you do?
So I knew that the rate of the volume changing, so dV over dt is equal to -2.
How do you know that was dV over dt?
Because it says, because it says 2 meters cubed, so like meters cubed means.
Okay, so we saw cubic units, so we know they're telling us about a volume. So they're mentioning how the volume is changing. You put a -2 because?
It's decreasing.
It's decreasing. The water is leaking out, so the volume is actually getting smaller. So you know that's a minus sign. This is why read is very important, right? You have to properly label your diagram, and you have to pay attention to all these little nuances here. Like there's a cubic meter unit, that means volume. The fact that the water is leaking means the volume is decreasing, so that should be a negative. If you forgot any of those things, that's not going to be good. Okay, what else? Do we know?
I did like a similar triangle thing, so I'll know that later.
Is this the only thing that we were told? The only rate we were told? Yes.
Yeah.
So what do you want?
We want dr dt when r equals 1.
So what's the 4th step here?
The equation.
You come up with an equation. How are you going to come up with the equation?
Well, they give you one already, which is v equals 1/3 pi r squared h.
Okay.
For the volume. But since we don't have anything relating to height, I use.
All right. We don't know about any DHDTs. Okay.
So I use similar triangles because if you look at the diagram,
Yeah.
the big triangle and the small triangle are similar.
Yes.
So you can use similar triangles to sort of like figure out.
What does similar triangles tell us?
the height so it doesn't really matter. So like the radius divided by the height of the first triangle is similar to the radius divided by the height of the second triangle.
Radius over height of the big triangle is equal to the radius over height of the small triangle. Okay, so that's going to be 3/9 is equal to, well, r over h, which means
1/3 equals r over h, which means that h equals 3r.
so h equals 3r. Okay, and then
you substitute 3r.
so you can plug that in.
And that becomes
So the 3's would cancel, and so the actual equation we want is going to be pi r cubed. Right? And then,
now you could differentiate explicitly to get the
well, that's the fifth step. We're going to differentiate. Implicitly with respect to time, because t is our variable, so we get
dv over dt is equal to pi times 3r squared times dr over dt.
And at this point, we know everything, right? We know the dv dt. We know that r is 1, and we want to find the dr dt. So that's step 6. Plug in, solve for your unknowns. So our dv dt is -2. Our radius is 1. And so now we can find our dr dt. So this is just going to be -2 over 3 pi is your dr dt. Does that answer make sense? Does it make sense to be negative?
Yes,
Why?
because as the volume decreases, the radius is also decreasing.
Right, as this goes smaller, the radius also gets smaller, so your radius is decreasing here. So that is how you do problem 7. Make sure you watch how you're labeling. A lot of mishaps can happen because of improper labeling. So that was problem 7. Okay, so now someone from the middle, tell me about problem 8. So, of course, step 1 is to read. We all know that. Step 2, diagram. I don't know if we need that, but let's read first to see if we need it. Okay. A man walks along a straight path at a speed of 5 meters per second. A searchlight located on the ground is 16 feet from the path. We start focused on the man. You could either have whatever. Okay. At what rate is the searchlight rotating when the man is 12 feet from the point on the path closest to the searchlight? Now, of course, we measure closest distance by perpendicular distance. That's what that means. Yeah, so someone tell me what's going on in problem 8. Okay, so this is the path that the man is on, I guess? Yeah.
And then below the path, a light.
Okay, so there's the light.
And then at one end, I draw a man over there.
Yeah.
And then I draw a perpendicular line from the light to the path.
Yes?
That's 16 feet.
So that's 16, because they said the light is 16. Yeah, the light is located around 16 feet from the path. So the perpendicular distance to the light from the path is 16 feet. Okay, yes. And of course the light is pointed on the man, so that's going to be the next thing. Okay.
And then from the man to the after the light is that's X.
So the distance here, we call that x, okay?
And I label the angle of the light theta.
Here.
And now I relate the theta by tangent theta equal to X over 16.
Hold on, wait, what do we know? What do we want? What information do we know?
Dx dt equal to 5.
Okay, so the man is walking along a straight path at 5 feet per second, so he's moved, this distance x is moving, enlarging at 5 feet per second, so that that's the speed at which x is changing. Yeah.
I think this one is the other way.
What do we want?
D theta dt.
We want d theta dt. When
Is 12 feet from the point on the
in terms of our variables, what is that?
X.
So x, when x equals 12. So that's what we want. What was their equation?
Tangent theta equal to X over 16.
So there was a right triangle here, and we had an angle in play, and the parts of the triangle that we had figured out were the opposite side and the adjacent side. Tangent equals opposite over adjacent seems to be like a pretty solid move here. Okay, now what?
I think the derivative of both sides.
Okay, derivative of tangent.
Secant theta d theta dt.
Let me write down. Step 5, differentiate. So this gives us secant squared theta d theta dt.
Equal to 1 over 16 dx dt.
Yes. dx dt over 16.
And now I know that when x equals 12, the hypotenuse is 20.
And x equals 12. So basically we are going to have 12 here, 16 here, not drawn to scale obviously. This side is going to be
20.
20. How do you know that?
3, 4, 5 times.
3, 4, 5 triangles. So the 16 is actually 4 times 4. The 12 is actually 3 times 4, which means you want this to be 4 times 5, the 3, 4, 5 triangle. I should probably write the 3 in parentheses to make this a little bit more suggestive. So the side that was length 3, I multiply by 4. The side that was length 4, I multiply by 4. Therefore, the side that was length 5, I have to multiply by 5, because this is going to be a similar triangle to the 3, 4, 5 triangle. So now we know that that side is 20. And yeah, what are you going to do with that?
And 1 over secant theta is 1 over cosine theta, and cosine of theta is 16 over 20.
Right, so the cosine of theta is 16 over 20, or it's going to be 4 over 5 when you reduce that. And then we're going to square that, and then we're going to put 1 over that. So this is going to be 5 over 4 squared is what the secant is going to be. D theta dt we don't know. Dx dt we know is 5. So now you just solve it. That's just an equation. I mean, technically we're doing step 6 here, plugging in phase. So we can multiply both sides by 16. That's going to die, and then we're going to divide by 25. And here we're thinking in radians per second. So that's 1/5. And that makes sense because the angle is increasing, so we should be getting a positive number here. Problem 9, someone from section 3. Yeah.
Diagram, right triangle.
Well, hopefully someone in the group completed, so you can start it off and then we'll tag someone else to finish up if necessary. So the first step is to read. Second step, diagram. What did your diagram look like here?
Alright triangle.
Come again?
Alright triangle.
A right triangle?
Like A at the top. Oh. Alright, it would be down there. But just turn it, rotate that shape 90 degrees. Top side.
You did it like this?
Yeah.
Okay.
So A was the top left corner, ship A.
A is right here.
And ship B was the top right.
B is right here. Okay.
And the hypotenuse is X. And I put 20 on the left side, 20 miles per hour.
20 miles per hour where?
Because A is traveling south. On the left side of the triangle.
So you put 20 miles per hour?
Yeah, and 80 miles between A and B. And what we know is that the distance between
Okay, so let's just read the question for the record. At noon, ship A is 80 miles west of ship B. At this time, both ships set sail. Boom. Okay. Ship A is sailing south at 20 miles per hour, while ship B is sailing north. So A is moving down, B is moving up at 10 miles per hour. How fast is the distance between the two ships changing?
you should draw an arrow of B going up. And write 10 miles per hour. And instead of a hypotenuse, it should be like connecting the bottom of A to the top of B. Like that. And that should be it. That's what you draw, guys. There you go.
Okay.
And then we listed our known variables.
Okay.
What we know that, but we could call the distance between A and B be lowercase b. So we know that dv dt is times
Distance from A to B, what is that?
the distance from A to B is no. That's not true. Give me a second.
Anyone else can start with the diagram here?
You make a right triangle with A on the left side, B on the bottom right.
I mean, so far, is this labeled?
I mean, you should probably bring down like the horizontal line to the bottom, so we can make a big right triangle.
Okay.
Okay? And
Otherwise, is the labeling good? Yeah?
If you took this approach, could you use the similar triangles?
Let's start out with the question I just asked. Is the labeling good? Yeah.
I mean, the value written there, 20 miles an hour, 10 miles per hour,
Yeah.
those are actually the rates.
Those are rates, so you wouldn't put them on the diagram because they're not lengths.
So,
So you wouldn't label the miles per hour at all. Okay. So let's say this was the starting point. Ship A was here, ship B was here. What can we label? So we know the distance between them was 80 miles. Now that's not going to change because they're moving vertically, so the horizontal distance between them is not going to change, so that can label 80. Okay, so ship B is moving up, right? And so let's say that's the current position of ship B. And ship A is moving down. Let's say that's the current position of ship A. Okay, what do we do? Yeah.
I labeled it D1 and D2 for A and B, but you also have to put T in front of it, which accounts for time, because they set off at noon.
So you label it what?
D1 and D2.
D1 and D2? Where's D1 and D2?
I just selected.
You mean these here?
Yeah. Yeah.
Okay. I mean, it's you X and Y. Okay, so that's X and that's Y. We label it with variables because they are changing. The ships are moving. Okay, now what?
Now you could, what's it called? The thing you're trying to find is the distance between the two ships.
Yeah.
And the shortest distance would be the hypotenuse.
Okay.
So I drew a line between that.
You mean connecting A and B?
Yeah, connecting.
Technically, it's not a hypotenuse yet.
Yeah. And what's it called?
Did you
And
label that?
Yeah.
What
And
did you
I
label?
labeled that line
Let's
C.
go with Z and X, Y, Z. Okay.
Okay.
Yeah.
And then now you could see that it's a right triangle if you what's it called? And that.
Well, we can take Andrew's suggestion and I think kind of realize that if we shift this down, it's going to stay 80. So we have a new right triangle here. We did a different color here. So now what the focus is this blue right triangle with the green hypotenuse. Blue hypotenuse. So in fact, this length here is 80. What is the height of this triangle? X plus 1. And the hypotenuse is Z. So that's a much nicer diagram. We don't label speeds on the diagram. The diagram we label the lengths, and we make sure that whatever length is constant, we label with a number. Whatever length is not constant, we label with variables. Okay? So that is okay. Now in terms of these letters, what do we know? What do we want? Yeah.
We know the value between the initial value between the two boats, which is 80.
Yes.
Yeah, and we also know the rate at which x and y are changing,
Which is?
which is 20 for x and 10 for y.
How do you write that down?
Okay.
dx dt is equal to 20, dy dt is equal to 10, right? Because it's a ship A is sailing at 20 miles per hour, ship B is sailing at 10 miles per hour. Okay, so that's fine. What do we want? We want dz dt. When, how would you define that? When t equals 2, sure, but how would we describe that in terms of x and y? Yeah.
X is equal to 40 and Y is equal to 20.
X is equal to 40, y is equal to 20. Explain?
They're moving at miles per hour, so it's 2 hours past.
Yeah, 2 hours past, because it's mentioned at 2 p.m. So we know they start at noon. We want to know how fast the distance between the two ships is changing at 2 p.m. if they maintain constant speed, which means they've been going for 2 hours. So if you're going for 20 miles per hour for 2 hours, you would have traveled 40 miles. If they're going 10 miles per hour for 2 hours, you would have traveled 20 miles. So that is what we know, that's what we want to find. So for equation, yeah.
It's the Pythagorean theorem would say a squared plus b squared equals c squared.
Right.
But in this case, it's going to be a squared because that's a constant.
Yeah.
Plus in parentheses 40 plus 20 squared.
No.
There's going to be a
We are not in the plug-in phase yet. Plug-in is step 6. You shouldn't be plugging in anything at step 4. 5, we are going to differentiate. It doesn't really matter, but let's turn this around to z. Z squared equals a squared plus x plus y squared. Differentiate. Derivative of the left side. 2z dz dt. Derivative of 80 squared? 0. Derivative of this?
2 x plus y times x prime plus y prime dx over dt plus dy.
So we have that. So in fact, we want dz dt, we can solve for it. So in fact, 2 can cancel on both sides. So our dz dt is going to be equal to x plus y times dx dt plus dy dt all over z. And do we know all those? Yes. So dx dz dt is going to be x plus y. It's going to be 40 plus 20 times dx dt times d plus dy dt all over, what is z? Huh? It is 100. Just give me the quick explanation here.
Because you basically plug in all the values for the initial equation you had.
Yeah.
X plus y becomes 60, and you get 6,400 plus 3,600, and you get 10,000, and the square root of that is 100, so z equals 100.
So x plus y becomes 60. So we have 80 squared plus 60 squared equals z squared. Okay, and you did what?
And then you add those values together, it becomes 6,400 plus 3,600, which gives you 10,000.
Sure, or you can realize that this is 20 times 4 squared. This one here is 20 times 3 squared, so z must be 20 times 5 squared. In other words, your z is 100. Yeah, so that's that. So this is going to be 60 times 30 over 100. All the 10s cancel out, so 3 6s. 18 miles per hour. That's how fast the ships are moving away from me. Questions on that one? Do you want to do a couple more? I mean, I feel like we did the hardest ones. Maybe problem 12, and then we wrap this up. Problem 10 is also a nice one. These are good test problems here, like 7, 8, 9, 10, 12. Probably something I'd put on a test. Like a quiz, like problems 1, 2, and 3. 1, 2, 3, 4, 5. Yeah, the rest of them are kind of like, maybe I'll throw 1 or 2 of those on a quiz, but like on a test, it's like 7 onwards. It's like test stuff. So maybe let's do one more. Let's try number 12. And we'll work on this one together. Teamwork makes the dream work. Okay, so 1, let's read. So, a baseball diamond is a square with sides 90 feet. Batter hits the ball, runs towards first base. So, it's a baseball diamond. They described it as a diamond, so we know that's that. But for those of you who aren't familiar with baseball, this point here is called the home. Let's say that's where the person bats from. He would run counterclockwise. This point here is called first base. This would be second base. This is third base. And so you run around. And we know the side lengths, so these are all 90s. So we can fill that in because that's a constant. So this length is 90, that length is 90, that length is 90, that length is 90. Okay, now what? What do we care about? What are we measuring here? So a batter hits the ball. The batter would be at home when he hits the ball. And then he runs to first base. And he's moving with a speed of 24 feet per second. That's really fast. Okay, so yeah, how do we put that on the diagram? Okay, so what does that represent?
Well, A is asking for the distance, and he's halfway to first base.
Okay,
So that's his position at that time that we're looking for.
so this is the position of what?
The runner or the batter.
So this is the batter. Okay, how do we put that into the label?
What about?
Is the batter stuck in time? Huh? No, he's running. So how do I account for that? Huh? How do I account for the fact that he's running? Yeah?
You would use a variable, so like you can mark the distance from the batter to first base as like A, and then the
Okay,
distance.
so let's call this distance here, you said A.
And then the distance from home to the batter is 90 minus 10.
So that length here would be 90 minus A. Okay. And what do we actually care about? So and what do we know about A? Well, we know that dA dt is 24. Or the way you labeled it, it would be minus 24, right? Because he's actually running that way. So the A is getting smaller.
Oh, yeah.
So you have to be careful with that. Okay. So it was probably nicer to label it the other way, but it's not going to matter. Okay, so part A. At what rate is his distance from second base decreasing when he is halfway to first base? So what do we care about here? How do we put that into focus? Yeah?
You can draw a line between the position of the batter and second base.
So here's second base. Connect that, and that's going to be his distance from second base. So what do you want to label that one? C. But the important thing is you labeled it with a variable, because it is actually moving. Okay. All right. So there are two parts here. There are two separate related rates problems. So let's actually talk about part A. Okay. So what do we know? What do we want? Well, we know dA dt. Minus 24. We want, well, dc dt. When
A equals 45.
when A equals 45. Equation.
Should we also call 90B?
Huh?
Should we call 90B?
Called 90 what?
B?
This?
Yeah.
No, because that's a constant. So the baseball, the shape of the baseball diamond he's running around isn't changing. Right? What's moving is this point. This guy is running, or the point is running around this shape. The shape is not going to change. So that's 90. That's actually going to always be 90. Yeah?
So you do A squared plus 90 squared equals C.
Right, Pythagoras' theorem again, because the baseball diamond is a square, so that's 90 degrees. The C would be the hypotenuse, this leg will be A, that leg will be 90. So we know that C squared is equal to A squared plus 90 squared. It's going to be the equation. And then, of course, 5, just differentiate. That is going to be 2C dC dt is equal to 2A dA dt. Derivative of 90 squared is 0. So we can find dC dt by A dA dt over C. And so now we go to 6, we're going to plug in. So dC dt is what we want to find. We go into that. A, we actually know is 45. dA dt, we know is minus 24. C, come again? Right, so let's actually calculate that, because that doesn't sound like a 3, 4, 5 triangle to me. So when A equals 45, what I have is that C squared is going to be 45 squared plus 90 squared. So that's going to be 2 times 45. What I can do then is I can factor out a common 45 squared, and I'd be left with 5. And then I take the square root of that. So that means your C is going to be 45 root 5. Right? And so now we plug that in. 45 root 5. And so 45's cancel. And we get minus 24 over radical 5. And feet per second. Which is decreasing. So we have a negative. That actually makes sense because C is getting shorter as he runs towards that. Questions on this one? Yeah. The value for A squared? Oh, because it says, we're looking at part A, right? So it says the rate at which his distance from the second base is decreasing when he is halfway to first base. So this is 90. So when he's halfway, that's when this length is 45. So I just plug in A equals 45.
When you broke it up, how'd you know multiply by 5?
How do I know to multiply by 5?
Yeah,
Where?
like 2 times 45, you broke that. You broke 90 squared to 2 times 45, but how'd you know that c squared was 45 squared times 5? Like, where did that 5 come from?
Factor, I factored. So if I have 45 squared plus 2 times 45 squared, that is 45 squared plus 4 times 45 squared. 45 squared is a common term, factor out the common term. I do that with 1 plus 4, which is 45 squared times 5. I factor, because we're not allowed to use calculators, so sometimes doing arithmetic like you're doing algebra is better. I don't want to have to calculate what 45 squared is. So I just thought of 90 as something times 45, which I could to make it a common term to factor out. It makes the calculations easier. And then when I square root both sides, just square rooting each individual, because that's how radicals work. We actually did exponentials and logarithms. You get the 45 radical. Or you could square 45 and then square 90 and then get these big numbers and take the square roots, but it'll be a lot harder.
So,
But
I was gonna say, 45 squared, or times 5 is a constant, why didn't you just?
yeah,
Oh, never mind, I was.
yeah. Then I square rooted both sides. So c squared was this, and I square rooted both sides. Okay. So we're going to do part B, which is the same. It's a similar diagram, but here in part B, they care about his distance from third base. So that's actually this one. So if we're doing part B, and I can call that something else. I can call that D. And we just want to find dt. That will look very good. Okay, let's call that. So it's going to be very similar. So like on a test, I'd ask either part A or part B. I wouldn't ask both, because they're very similar ideas here. So here, what I know is I know, and you could relabel this as A to do it, but let's just keep what we know so far. We know that dA dt is minus 24. We want dE dt when A equals 45. So I'm going to set up Pythagoras' theorem with that. So that means E squared is going to be equal to 90 squared plus 90 minus A squared. Differentiate that. 2E dE dt is going to be 2 times 90 minus A times dA dt. So dE dt is going to be 2 times 90 minus A dA dt all over E. And now I can plug those all in. So this means dE dt is going to be 90 minus 45 times minus 24 over E. And E, now this is going to be symmetric, so I also know that E is going to be 45 radical 5. Figure it out as in part A. Because you'd have a symmetric diagram here. So we'll just do the calculations I did with the left side. And yeah. So that's going to also be a 45. Something is off here.
Isn't it the negative dA of dt?
Yes, because technically here, well, I was using this triangle, so I actually want this distance. So it's going to be weird to write it like this. We probably should relabel, but it's actually going to be the derivative of the side that goes 90 minus 8. Or you could just relabel it as 8. And that is actually increasing by a positive 20. You see, paying attention to the signs can actually save you here. Those two are going to cancel. You would get positive 24 over radical 5 feet per second. Yeah, so wrap up there. So we did not do problems 5, problem 6, problems 10 or 11. You should really try those on your own. Make sure that you have this down. But we're actually going to move on. But that's related rates in a nutshell. As you can see, we always do the same 6 steps. So while these will be like word problems, some of them will look pretty hefty. They're easy in the sense that the strategy is kind of laid out for you. You know you're going to approach all of them in the same way. So you can finish up what we haven't done. That will be some good practice as well as going through some homework. And other than that, we're going to move on. I want to talk about, so the next big topic is going to be maximum minimum values, but I actually want to take a pit stop before that and talk about differentiating inverse functions. I don't know how much background I want to give here though. You would have covered inverse functions in pre-calc. Anyone can tell me what an inverse function is, basically? What's an inverse function? Let's say you have a function. What's an inverse function? Huh? Huh? I have a function f of x. Tell me what its inverse is. So we're going to differentiate them. We need to actually know what they are. So let f from a to b be a function. Okay, so that's just notation I am talking about here. A is representing the domain of the function, and B is representing the codomain of the function. The inverse of f, if it exists, it might not exist. I'll tell you when it does or doesn't. Is another function denoted. Do you remember the notation for inverse functions? Right, it's f raised to the negative 1, right? Which causes all sorts of confusion, but we'll talk about alternative notations in some situations. Now, what is the domain and range of f inverse? Right. It will have domain B and codomain A. So this is a function that goes backwards, at least in relation to f, such that, how do you know a random function that goes from B to A, how do you know that it's an inverse or not. What makes an inverse? So here's our set A, here's our set B. F is going to take someone from over here, put it over there. What does an inverse do?
It takes B and gives to A.
It takes what?
Takes from B and it gives you the output of A.
Any random thing? Any random function I come up with that goes from B to A? So the inverse is just a function that reverses f. So it's not just any function from B to A, it is the one that undoes the rule for f. So if there's an x here, and f takes x to an output f of x, then what the inverse function would do is it would take that f of x, and it will give you back the original x. So it doesn't just go and pick anyone here. It picks the guy who was the original input. And we call the function that does that f inverse. It undoes the function. Another way to write this is to say that if you take f inverse of the output of the original, x is going to be the answer, right? So f is going to do something to x. F inverse applied to that output is going to undo whatever the original function did. So it's going to give you x for all x in the domain of f. Now, it's worth note this relationship is symmetric. Now, I'm not going to prove it, so that is a theorem, that is something that you'd have to prove. So, it would also be true that f of f inverse is also going to be x, but this will work for all x in the range of f, or equivalently, you can say or for all x in the domain of the inverse. So that's what an inverse function does. A function will do something, an inverse function, if it exists, undoes all that stuff. Now, not all functions have inverses, and this is going to explain some of the peculiarities that we will see when we look at inverse trig functions, because there are two properties that a function must have in order for it to have an inverse. So not all functions you are able to actually do this undoing kind of thing with. So let's look at some definitions. We say f from A to B is 1 to 1, or I write 1-1, or one word for it is injective, if you want to sound all fancy. If distinct inputs give you distinct outputs, you can state this as an equation by the following. If the output at x is equal to the output at y, then the x must be equal to the y. F of x equals f of y implies x equals y. Equivalently, if your x is not equal to the y, so if you have different inputs, they will have different outputs. Your f of x is not going to be f of y. Now, what does a one-to-one function look like exactly? Well, as a mapping diagram, it's going to look like this. So one point here will connect to one point there. And then another point here is going to connect to someone else. Another point is going to connect to someone else. Now you might have other people who are not connected, that's fine, but the point is that there's only one line coming from here to each guy there. Now you do not have, now in general, two things can go to the same thing in a function, but not in a one-to-one function. This is a one-to-one function. You could have something like, this guy goes to that guy, and another guy goes to the same guy. This is not a one-to-one function. So you have functions that look like that. So an example, y equals x plus 1 is a one-to-one function, whereas y equals x squared is not a one-to-one function. What you'd realize is that here, if I plug in 1 or negative 1, they both give me the same output 1, right? So I would have 1 and negative 1 both giving me 1 as the output. So I have two different things going to the same thing. That's not one-to-one. This is called a many-to-one function. Many things going to one thing. But we don't want functions like that. We want one-to-one functions. Each guy in the domain is connected to a distinct guy in the range. We don't have reusing of inputs. One way you can tell from the graph that something is one-to-one is if it passes the horizontal line test. One-to-one functions pass the horizontal line test. This is the test that says any horizontal line crosses the graph of the function at most once. That's the horizontal line. You will notice for this graph, that is actually true. Y equals x plus 1, that's just a straight line like that. Now at any point that I draw a horizontal line, it's only going to touch that function in one spot. Whereas with the y equals x squared, I can draw a horizontal line that touches in two spots. That's more than one. I could also draw a horizontal line that touches in one spot. That might be like this guy right here. But the fact that there exists some line that will touch it more than once, that means it's not one-to-one. Functions in general, they all pass the vertical line test, but there's a special type of function that also passes the horizontal line test. We call these functions one-to-one or injective. Now, one thing you would want to notice here, note, if f is not one-to-one, it can't have an inverse. Well, why can't it have an inverse? Well, let's say I have two things here heading to one thing over there, right? So now if I try to flip this the opposite way and think of a function going from here to there, what's going to happen? This is going to be the input. What's the output?
Just one of them.
Yeah, but which one? I didn't put any positives or negatives here. Means you don't know. You can't know for sure, right? There could be a bunch of things heading to this one point. What is going to be the output for that guy if I flip the function around? I don't know. Pick at random. That's actually pretty hard to do, by the way. You need like a whole axiom of choice to be able to do that, and that's a controversy you'll deal with when you get to like advanced calculus or real analysis, so let's not worry about that now. The idea is you will not be able to define the inverse function. You won't be able to say, oh, when I take this input, that's the output. You would have to say, oh, when I take this input, well, the output could be any one of these, I don't know, right? It's not a nice way to define a function. Like, you don't know how to undo this function. It could be anything, right? And a lot of times, especially after you simplify, you can do anything. So if I were to pretend, for example, that y equals x squared has an inverse, and I tell you, oh, the output is 1. Okay, tell me what is the output of the inverse function if I plug in 1. Well, I don't know for sure. It depends which one of the inputs it came from. Maybe it came from the negative one, and the output will be negative 1. Maybe it came from the positive one, the output will be positive 1. It's not a well-defined function. The inverse function cannot be well-defined going the other way. We want to know that once we take an input, we can get that input back, right? And it won't depend on someone randomly picking something. It's not, would not be well defined in this case. Right? You won't know how to undo the function because there will be too many options. And who would know how to pick properly? Like, I didn't know what you had in your head as the original input. You know what I mean? And that's a problem. Now, there's another important property of a function.
Question?
Yes.
Is sine 1 to 1?
Is what?
Is like the sine function 1 to 1?
Does it pass the horizontal line test?
No.
Exactly. So no, it is not.
So how come
So sine would look like this. I can draw a horizontal line that does not. That touches it an infinite number of times. That's way more than 1. So no, the sine function is not 1.
So how come it has an inverse?
We will get to that. That's what I said earlier about when we get to inverse trig functions, there are some peculiarities I want to deal with, and I'm telling you why these were peculiarities we had to deal with in the first place. So yes, the trig functions as they exist, sine, cosine, tangent, they are not invertible in their current state. We actually have to tweak them a little. And that's why the graphs of the inverse trig functions are going to look the way they look. So I'm building up to explaining them. So first of all, not being one-to-one is a problem. Let's talk about another definition. F from A to B is called onto. Another word, if you want to sound fancy, surjective. If every, and I do mean every element in B is the output of some element in A. Now you might think, isn't that always true? No, there are functions for which that is not true. So, what it means is, in an onto function, if you have 4 guys over here, there's at least 4 guys over here that will connect to everybody over there. You can't have someone left out, right? Everyone has to get picked. Now you can have several guys go into the one guy, but the important thing is, there's no one left over when all the connections are done, right? So, i.e., the range is equal to the codomain. Now remember, codomain is just the set that we're choosing connections from. But if you do this in such a way that you use up every single person in the codomain, we say you've made an onto function. So that's onto. Not onto means we have 2 sets, and we're connecting to some people, but there's someone left over that no one has connected to, right? So an example here is y equals x squared is another example. If I think of f with domain R and range R, and I think of it as f of x equals x squared, then that's not going to be onto. How do I know? Because the real numbers include all negatives. none of the negatives will get hit, right? So I would have a bunch of negative values here. There are a bunch of things here that aren't the output. What input gives me the output -1? None of them, right? Not with a real value function anyway, right? So none of the numbers down here get hit. Y equals -5 will never be an output of this function. So if I think of the real numbers as the codomain, there are people who are left out by the function y equals x squared. No one is going to be left out with y equals x plus 1, the previous function I mentioned as well, right? So this looks like that. Tell me any y value you can imagine. Pick a random guy down here. Okay, there is an x value that will give me that y value. Pick a random value up here. Hey, okay. That x value is going to give me that y value. Everyone that is actually a member of your codomain will be the output of somebody. You can find someone that is the output. So this means F is onto if for all y in B, there is some x in A such that if I plug that function into x, y will be found. Now here's something to note. Note, if f is not onto, it cannot have an inverse. Why not? Well, by definition, a function is a rule that assigns to every member in a set exactly one member in some other set. So the first set is called the domain, the second set is called the range, or the codomain. So if I have a function doing its thing over here, and I have someone missing, it means if I were to flip this around and think of that as the domain, it wouldn't define a function at all. Because a function would have to assign to everybody in the domain. A function doesn't leave anyone out of the domain. Every domain element has to have an output, right? So here, if this is the domain, well, this set can't be a domain. This set cannot be the domain of a function. Since there would be a domain element with no output. And that contradicts the definition of a function. A function is a rule that assigns to every member of one set, called the domain of the function, exactly one member in another set, called the codomain of the function. Now, in the event that all outputs are unique to the inputs and all outputs are actually selected, we can say a function is one-to-one respectively onto. And here's another theorem that I will not prove for you. But it turns out that these two things are the only things we have to worry about when it comes to invertible functions or finding an inverse. F is invertible, meaning its inverse exists. If and only if, that's not a typo, I'm actually typing it with two F's. So if you ever read that in a math book, it's not a typo. This means if and only if. F is one-to-one and at the same time onto. That is a theory. How do you know an inverse exists? You check if the function is one-to-one. Does it pass the horizontal line test? Then you check if it's onto. Is everyone in the codomain an output of someone in the range? Once you have something that's one-to-one and onto, that is completely reversible. without ambiguity, right? So if I have everyone connecting to one other person, right? There's no doubling up and no one's left out. If I were to ask you, what is the original input here? Well, it's that guy, without ambiguity. What is the original input here? Well, it's that guy, without ambiguity. You'd always be able to make the connection in the reverse order and not miss anyone. So now, there's a few more properties I probably want to talk about. Well, I didn't have in my notes to talk about it, but I will talk about it next time, I guess. But let's actually deal with Michael's question. What the heck is going on with sine? We know we have a sine inverse. Does it not exist? Well, here's how we deal with the inverse trig functions. Sometimes there is a function that is not one-to-one or onto. So there's this idea of restricting the domain of a function. So pretty much if we look at a function in its entirety, it is not going to be invertible, but maybe you can cut off a little piece of that function that's going to be invertible. A couple of examples. We already saw that y equals x squared, not one-to-one, not onto. But if I were to just, you know what? I only care about the right side of this function. So from 0 there. And I only care about, so set the codomain to be only the non-negative reals and set domain to only be the non-negative reals. Then that function will be one-to-one and onto. The right side alone will pass the horizontal line test. And if I pick any positive y value, there's going to be some x value in that y value. So I can restrict the domain. Just look at a piece of a function at a time. And within that little piece of the function, I can have the one-to-one and onto condition, and I can reverse the function in that region. So, namely here, if my f of x was x squared, then my f inverse here will just be the positive square root of x. Whereas I could do the same thing with the negative side and just take the inverse be the negative square root of x. There will be no ambiguity there. I'll know exactly what number to pick. We do the same thing with sine and cosine. So if you look at y equals sine of x, now in general, this guy does not pass the horizontal line test. So what we normally do, which is why in your textbook it always tells you this restriction from minus pi over 2 to pi over 2. What we actually do is we think of the function here, pi over 2, and the function here at minus pi over 2. And we only care about the piece of the function in between these 2 points. So in other words, we ignore everything else. We think of the codomain as only the y values between plus and minus 1. And basically, just within that little window, this is a completely reversible function. It's one-to-one, and I can find all the original inputs if you tell me an output. And so now what we can do is we can actually graph. Do you remember how to graph inverse functions? You reflect in the line y equals x. So pretty much you imagine there's a line up here, and you flip this, and so what we get is when we look at the sine inverse of x, it's just going to look like this. So if you look up the graph of sine inverse, that's what you're going to see. Now, this point here, now remember, the x's and y's switch positions. So this, before there was a pi over 2, this was the positive 1. Now this is going to be the positive 1. That is going to be the pi over 2. Before over here, this was the minus pi over 2. That was a negative 1. So this is going to be the minus pi over 2. That is going to be the negative 1. And so that is the sine inverse function. It is just a sine with a restricted domain. And so we can say sine inverse exists, but it only works, it only gives us output between minus pi over 2 and pi over 2, and only takes inputs between from negative 1 to 1 inclusive. So the domain of this guy is from negative 1 to 1. The range of this guy is minus pi over 2 to pi over 2. We'll stop there. We'll talk about how do you get the graph of cosine inverse and tangent inverse next time, as well as how to differentiate it. Then we'll do a bunch of examples. So our next quiz is going to be next week, Monday, right? So no quiz this week. And it's going to be on related rates and whatever I finish